You might be new to Kubernetes, or you might have been working with it for a while. No matter your experience level, you might not be aware of all the Kubernetes Workload APIs. There are pods, of course, at the very low level, ReplicaSets and jobs somewhere in between, and deployments, StatefulSets, DaemonSets, and CronJobs on the top. To make things more complicated, those are workload APIs baked into Kubernetes clusters, and on top of those, we can have more, much more, much more. Today we will explore all of those. We'll see what is the purpose of each, what each of them should or should not be used for, and quite a few other things. Buckle up, we are about to dive into all Kubernetes workload resource types. We'll take a quick break to introduce you to StatusPal, the sponsor of this video. You do have incidences in production. Everybody does. We cannot avoid failures. What we can do is recuperate from those failures fast. And a big part of that lies in the ability to communicate what happened and why it happened to the rest of the team and to the end users. That's where StatusPal comes in. It has integrated monitoring. It supports incident automation from external monitoring tools. It allows us to send notifications to almost anything. It is developer friendly, and there's so much more, and I invite you to check it out. There is a special link with the discount code in the description over there down. Big thanks to StatusPal for sponsoring this video, and now let's go back to the main subject. Containers are the base of everything running in Kubernetes. Everything ends up either running in a container or being managed by something running in a container. No, actually, that is not true. It does not have to be containers. It could be WASM, or it could be VMs managed by KubeVirt, or many other ways to run processes. Nevertheless, if we are talking about vanilla Kubernetes, it's all about containers. We package processes into container images and we run them as containers. However, you need to pay attention to this one. We cannot run containers directly. There is no option in Kubernetes to say, run this container. Containers are always wrapped into pods. Hence, that is our starting point. Let's take a look at what they are, how they work, and why you are unlikely to ever run them directly. Pods are the base of Kubernetes resources. Any type of a workload, at least among those baked into Kubernetes, ends up being a pod. So, what is a pod? A pod is a collection of one or more containers. Most of the time, a pod contains a single container with your or someone else's application. On top of that, there might be additional containers for various purposes. For example, a service mesh might attach a container that deals with networking. Those additional containers, most of the time, are called sidecar containers. Here's an example. That is a pod manifest containing a list of containers. In this case, there is only one based on the silly demo image. It has a name, a list of ports, a readiness probe, the one that is used by Kubernetes to deduce whether it is healthy, and resource limits and requests that are used to deduce how much memory and CPU we expect it to use. Now, if we apply that manifest and retrieve all the pods in that namespace, we can see that it is running. We sent a request to Kubernetes API to apply a manifest containing a pod with a single container. As a result, Kubernetes started running that container wrapped inside a pod. That's the container with our application. Here's the thing though. You will probably never run pods directly. That would be foolish, since pods alone are not fault tolerant, they are complicated to replace with new releases safely, and so on and so forth. Pods are building blocks that should be managed by other types of workloads. Here's an example. Let's say that something happened to a pod. Let's say that it crashed, that it disappeared. What would happen in that case? We can simulate that by, let's say, deleting the pod. You can probably guess what happens when we delete something. It disappeared, it's gone, and it's not coming back. Never, ever. Now, if that was our intention, that should be the expected outcome. But what if that's not what we wanted? What if our goal is to have that pod running forever and ever, or until we choose to replace it with a newer release? What if we would like to have some kind of a contract that says run this pod no matter what happens? In that case, we would need something else. We would need a replica set. A replica set is a Kubernetes resource that ensures there is always a stable set of running pods for a specific workload. It is a special type of resource that ensures that the contract between you and Kubernetes is maintained. It is a resource that allows us to say, I want this number of pods with those specifications. Make sure that it is fulfilled no matter what happens. The world might end, but those pods should still be running. Here's an example. This is a replica set very similar to the definition of the pod we explored earlier. The container section is exactly the same. The difference, however, is that the spec is now part of a template. We are telling ReplicaSet how to create pods rather than what pods are. ReplicaSet is a controller that ensures that pods we want are the pods that will run forever and ever. A second difference is that this time we have an option to specify the number of replicas. So we are not only saying this is the template to create pods, but also that is the number of pods I want. No more, no less. Now let's apply that replica set. The easiest way to see what's happening is through the kubectl 3 plugin. So let's use it. That plugin allows us to explore ownership relations between Kubernetes resources. In this case, we can see that the replica set created 3 pods and it now owns them. It is responsible for them. It is making sure that the contract is maintained, meaning that it is ensuring that 3 pods based on the template we specified are always up and running. More or less. You will see that that's not really true, but we'll get there. All in all, we sent a request to the Kube API to apply a replica set. Since that replica set did not exist, Kubernetes created it. The replica set controller detected a discrepancy between the desired and the actual state. We said that we want 3 pods, and there were none, at least none owned by that replica set. Hence, the controller created 3 pods based on the template we defined. And we can confirm that is indeed the case by deleting one of those pods and then retrieving the replica set and the pods it owns with kubectl 3. We can see that there are 3 pods, one of them being created a moment ago. That is the fulfillment of the contract in action. ReplicaSet manages pods by continuously watching their state and reacting if it differs from what was specified. As a result, it created a new pod to replace the one we deleted. So, when we removed the pods, the ReplicaSet detected discrepancy between what we want and what something is and created 3 new pods. Similarly, we can use it to scale up and down. Let's take a look at the diff between the manifest we applied and a slightly modified version. We can see that the only difference is that the new manifest has 5 instead of 3 replicas. You can probably guess what will happen if we apply it, but let's do it anyways. This time we can see that there are 5 pods managed by the replica set. So we changed the number of replicas in the manifest and sent it to Kube API, which resulted in the updated replica set running in the cluster. That replica set noticed that the desired state of 5 replicas is not the same as the actual state of 3, and it created 2 new pods. Now, there is one important note here. ReplicaSet ensures that the desired state specified in the spec is always the same as the actual state, except for the template. Template is used to create new pods and nothing else. ReplicaSet does not ensure that the state of the pods created with the template is always correct. And we can demonstrate that with the modified version of the manifest. So let's take a look at the diff. We can see that the tag of the image changed from 115 to 116. Now, let's see what happens if we apply that manifest and retrieve the dependency tree of the replica set. Judging by the age, we can see that no new pods were created or replaced. The replica set did nothing because we did not modify the specification itself, but the template used to create pods. And we can confirm that even further by retrieving the YAML specification of the pods running in the cluster. We can see that the image is still 115. The changes we made to the template were not applied since, as I already mentioned, template is not used to manage the state of the pods but only to create new pods. Now, try to guess what will happen if we delete all the pods managed by that replica set and retrieve all the dependencies of that same replica set. We can see that new pods were created. That was to be expected since, as we already know, we have a contract that the number of replicas should always be 5. We already saw that, and the reason for deleting the pods is not to demonstrate that ReplicaSet always maintains the spec, but what happens with changes through template. Let's retrieve YAML spec of the pods in the cluster one more time. We can see that this time the version is indeed set to the new one, to 116. The ReplicaSet detected that the number of running pods differs from the number of specified pods and created those that were missing. It used the template to do that. There's a thing though. Just as you will probably never run pods directly, you will probably not be creating replica sets either. We already saw that replica sets are limited when we change the version of the image in the template. We had to delete the pods for that change to be applied. That's obviously not ideal. We should have used deployments instead, and we will, but only after we delete the replica set we just created. Here's another lesson though. When we delete a Kubernetes resource, the controller behind it makes sure that all the resources that might have been managed by that resource are removed as well. Since the replica set was managing pods, they should be deleted as well. Let's double check that. It's all gone? Gone? There is nothing. There is no replica set and there are no pods. We deleted the replica set, which before disappearing completely made sure that the dependent resources were deleted as well. In this case, those dependent resources were the pods it created and managed. Only after the replica set controller deleted all the pods it owned, it removed itself from the system. Now, with everything gone, we can take a look at deployments. Deployments are almost the same as replica sets, at least when defining them is concerned. Let's take a look at the diff between the two I prepared. We can see that the kind changed. That could have been the only change, but I also added min ready seconds and strategy entries. Not necessarily because we needed those, but rather because those will slow down some processes we will explore later so that we can observe them more easily. Anyway, let's apply that deployment and take a look at the tree. On the first look, creating that deployment seems like a waste. The end result are the same 5 pods we would get if we created ReplicaSet directly. We sent a request to the Kube API to apply a manifest of a deployment. A deployment was created and its controller created a replica set. The controller of the replica set saw that pods are missing, so it created them as well. Now, let's take a look at one of the things that make deployments special. As we saw before, updating a template of a replica set does not affect existing pods, so changing the image tag did not produce the effect we wanted. Let's see what will happen if we do the same, exactly the same, with the deployment. Here's a diff of the changes I made to the deployment manifest. The only modification is in the image value, which now contains tag 117. A few things will happen if we update that deployment, so I'll execute kubectl apply followed with kubectl tree to output right away the ownership tree. Since I want us to see how it progresses, we will use vidi to output the tree every second. If you're not familiar with vidi, it is an alternative to watch. Anyway, here it goes. Deployment created a second replica set, which initially was set to have a single replica of a pod that uses the new image tag. From there on, it started performing rolling updates. It started reducing the number of replicas in the old replica set and increasing number of replicas in the new. At the end of the process, the old replica set was scaled to 0 replicas and the new one, the one with the new image tag, was scaled to 5 replicas. That was an example of an effortless rolling updates and is arguably the main reason why we use deployments. Here's what happened. We modified the manifest of the deployment to use image tag 117 and applied it to the Kube API. That resulted in updated deployment, which in turn realized that the tag changed and created a second replica set to have a single replica. The new replica set created a single pod. From there on, deployment started updating both replica sets. It was reducing the number of replicas in the old one and increasing the number of replicas in the new. As a result, the old replica set started removing pods while the new one was creating them. Eventually, all pods ended up being managed by the new replica set, while the old one ended up managing nothing, nada. The new version of the application was released safely and without downtime. Yeah. Now, there is one more thing related to deployments we need to explore. We need to talk about volumes, since they are one of the main reasons why you might choose not to use deployments. So far, we established that we should neither use pods nor replica sets. They are important building blocks and understanding them is important, but we can safely focus on deployments, which will create and manage those for us. But depending on the type of the application we have, deployments might or might not be a good choice. The main reason why we might use them or discard them lies in how they manage volumes, which are most of the time external storage. Let's take a look at yet another example. This manifest defines two resources. The first one is persistent volume claim. I'll explore volumes in one of the upcoming videos. For now, what matters is that persistent volumes claim is a way for us to claim a volume, to request storage that can be attached to containers in a pod. Further down, we have a modified version of the deployment we used earlier. At the very bottom of it is the list of volumes we would like to have. There's only one called silly cache, which references the persistent volume claim named silly claim. Inside the containers section, we are mounting the silly cache volume into /cache directory inside the container. As a result, all 5 replicas of our application should have external storage mounted. And here's a question for you. How many volumes do you think will be created for those 5 replicas? Do not answer that question aloud. It's not a good idea to talk to your monitor. Keep that number to yourself while we take a look at the result. Let's wait for a few moments until rolling updates are finished and take a look at the pods and persistent volumes that were created. As expected, there are 5 pods. If you see more, you're impatient and you did not wait until rolling updates finished. The number of pods does not matter right now. What does matter is that there is only one persistent volume. All replicas of the application, the pods, got the same volume attached. They are all sharing the same storage. So we sent a request to the Kube API to apply a persistent volume claim and the deployment. So those were created or updated inside the cluster. The deployment itself created a replica set which created 5 pods. Since the pods themselves were instructed through the template in the deployment to use the claim to request a volume, a persistent volume was created and attached to all the pods. Now, depending on the type of the application we're using, that might be just what we want, or that might be unacceptable. As a rule of thumb, stateless applications should be managed through deployments. On the other hand, stateful applications tend to have separate storage for each of the replicas as a way to avoid potential issues when writing files to disk. Hence, we need to look for a different way to run stateful applications. And we will do that right after we destroy the deployment and the volume we just created. StatefulSets are similar to deployments, at least in the way we define them. Here's an example. On the first look, this is almost the same as the deployment we used earlier, with three notable differences. First of all, there is no need to define a persistent volume claim. We will see later why that is so. Next is the obvious one, with kind being set to StatefulSet. Finally, the most important difference is in the way StatefulSets deal with volumes. While deployments specify which volume claims to use, StatefulSets define volume claim templates. That is similar to how ReplicaSets contain pod templates that allow them to create pods they need. Similarly, StatefulSets have volume claim templates that create volume claims for each of the replicas. In this case, we have a single claim template that is essentially the same as the persistent volume claim we had as a separate resource in the manifest with the deployment. What matters for now is that StatefulSets know how to create persistent volume claims, and that enables them to treat volumes in a very, very different way from deployments. Now, let's see it in action by applying the StatefulSet and watching the tree. Before we get back to volumes, there is one important thing we can observe. The names of the pods are, this time, predictable. We specify that we want 2 replicas of SillyDemo. Unlike with deployments, the names are predictable, and the order how pods or when pods are created and destroyed is predictable as well. Since we requested 2 replicas, StatefulSet created the first one with the name SillyDemo O, and then the second one called SillyDemo 1. So the names are predictable, and the order pods are created and, as you will see soon, destroyed is predictable as well. That is important when working with stateful apps like, for example, databases. Another note is that unlike deployments, StatefulSets do not create and manage replica sets. Instead, StatefulSets manage pods directly. Now, let's get back to pods and persistent volumes. This is the important difference. This time, containers in each pod got a separate persistent volume, a separate storage attached into them, into containers. Here's what we did and what happened. We sent a request to Kube API to apply a StatefulSet. Since that StatefulSet did not exist in the cluster, a new one was created. Since we specified that it should contain 2 replicas, 2 pods were created by the StatefulSet controller. In parallel, the StatefulSet created 2 persistent volume claims, which claimed 2 volumes and attached 1 to each of the pods. Now, let's see what happens if, for example, we increase the number of replicas. Here's the diff between the old and the new manifest. The only change is that the number of replicas jumped from 2 to 5. Let's apply that and watch the changes with the tree. StatefulSet continues working in an ordered and predictable manner. It started by creating the 3rd replica, SillyDemo 2, since 2 were already there. Then it created the 4th, or SillyDemo 3, and so on and so forth. As you can probably guess, even though we cannot see that on the screen, it also created 3 new persistent volume claims, which resulted in 3 new persistent volumes, 1 for each of the new pods. Finally, just as creation of pods is predictable, by always starting from 0 indexed pods, deletion is predictable as well. Depending on whether we reduce the number of replicas or delete this whole stateful set and all the pods it manages, deletion always starts from the one with the highest index and continues down towards 0. So let's delete the stateful set. Now I will leave it to you to observe how pods get deleted. Once you're done, we will explore a completely different, yet somehow the same type of Kubernetes workloads. The next Kubernetes workload type is DaemonSet. I already prepared the manifest, and instead of taking a look at it directly, we will explore the difference when compared with one that contains the deployment. There is the obvious change in the kind that is now set to DaemonSet, but also in some fields missing. It would make no sense to specify replicas, strategy, and quite a few other things that might be useful for deployments or stateful sets. Now, you might be asking, why? Well, let me show it in action before I answer that question. Let's apply the manifest and output the ownership tree. Now, this might look strange. The DaemonSet created 3 pods even though we did not specify any number of replicas. Why are there 3 pods and not 1 or 5 or any other number? To understand that, we need to output the nodes of the cluster. If we exclude the control plane node that typically should not have any workloads, there are 3 worker nodes. That can lead you to guess what the DaemonSets do. They guarantee that the pod will run in every single worker node of a cluster. Here's what happened. We have a Kubernetes cluster with a control plane and 3 worker nodes. We apply a DaemonSet, which in turn ensured that there is a pod based on the template in every single node of the cluster. If we would add more nodes to the cluster, the DaemonSet would ensure that a pod is running there as well. If we would remove a node, well, nothing would happen. We would have 1 less node, and with that node gone, 1 less pod. All that begs yet another why. Why would anyone want an instance running in every single node? Well, that's very useful for types of applications that are specific to nodes. An example could be log collection. Tools like FluentD run as DaemonSets since they need to collect and ship logs from each node of a cluster. A similar need exists for observability tools and many others. More often than not, DaemonSets are used by third-party tools, but there might be cases when your apps should also run on every single node of a cluster. However, we are not yet done. There are a few other workload APIs we should explore, so let's remove, gone, the DaemonSet and move on. The next in line is jobs. All the workload types we explored so far are meant to be used for long-running processes. If a main process in a container stops, the container itself would stop, and with it, pod would be considered unhealthy. If such a pod was created through a ReplicaSet, StatefulSet, or a DaemonSet, it would be recreated. All those resource types assume that the contract means that they should ensure that specific number of pods should run forever and ever. More often than not, that's exactly what we want. However, there are cases when we want to execute a process that does something and once it's finished, shuts itself down and disappears. A typical use case for such processes would be batch processing, pipeline builds, and other one-shot actions. Fortunately, Kubernetes has jobs, which are a type of workload designed to do just that. Let's take a look at yet another manifest. This is a job. It is very similar to other workload types or workload APIs with a template that allows us to define the characteristics that will enable it, the job, to spin up pods. The only notable difference is that we can set restart policy to be either never or, as is the case in this example, to on failure. As a comparison, deployments have that field set to hard-coded value always. That field alone gives a clear indication of what the job does. While pods created through deployments are always restarted or created, no matter the reason they failed, those created through jobs are either never restarted or only in case they fail. If the process running in a container ends running successfully by emitting status code 0, job that created it will make no attempt to start it again. Now, let's apply it and take a look at the ownership tree. A pod was created and it is no longer ready. And that's okay, since it completed doing whatever it was supposed to do, which in this case was to output "what is this" message. Now, even though the pod is no longer running, we can still access the logs it created. And there we go. We sent a request to Kube API to apply a job was created, and its controller created a pod. The container in that pod started the process that eventually finished doing whatever it was doing and returned exit code 0. That was it. Unlike other workload types or APIs, the job did not try to restart it or to recreate it. The job finished, so let's remove it before we move into our next workload type. Being able to run a job, as we just did, is often great when creation of those jobs is triggered by something. For example, if you would run CI/CD pipelines in Kubernetes, those pipelines will be jobs triggered by some events like pushing code to a Git repo, container images to registry, uploads to S3 drive, and so on and so forth. There are, however, cases when we do not have such triggers, but we would like to run jobs periodically. A good example would be scheduled backups. In those cases, we can use CronJobs. Here's an example. The kind is this time cronjob. It contains schedule that uses a standard Linux cronjob syntax to define frequency of execution and a job template. In this case, the job will run every single minute. Just as deployments are types of resources that manage ReplicaSets, CronJobs manage jobs. So, job template tells CronJob how to create jobs, and in this case, the content of the template is pretty much the same as what we had in the job earlier. So, let's apply it and take a look at the cron job inside the A-team namespace. You can probably guess what those fields mean. So let's watch the pods that should be created by that cron job. We can see that the first pod was created. Now let's fast forward to the next minute, and there we go. The second pod was created as well, and the third, and so on and so forth. We explored all workload resources baked into Kubernetes, but there is more, so much more. Baked-in resource types or APIs are only the tip of the iceberg. Now, let's destroy the cron job before we move on. Resource definitions baked into Kubernetes are more like building blocks than something we should use directly. We can accomplish so much more if we add projects that use those building blocks and provide higher level abstractions. Unfortunately, we do not have time to go through those today, especially since the number of those extensions and abstractions is close to infinite. We could be using Knative, Cloud Native PostgreSQL or CMPG and many other third-party CRDs and controllers. Or we could build our own. You can find examples of quite a few of such solutions in this channel. Now, before you leave, before you move on, I have a question for you. Was this video useful? Would it make sense to continue through other Kubernetes API groups? If it does, which one would you like to see next? Service APIs maybe? Config and storage APIs? Something else? Let me know in the comments. Thank you for watching. See you in the next one. Cheers.